So I'm from Parity. I'm working on a project called Polkadot, which in a quick, 30-second introduction, it's a blockchain designed for scalability and interoperability. The rough idea is that we have a root relay chain, which manages the advancement and security of various parachains, which have their own state machines and can communicate amongst each other. So the technology that we're using to build Polkadot is Substrate, but it's also a very general framework that essentially you can use to write any kind of blockchain. Because at Parity, now we've written a bunch of different clients for different blockchains, and we started to think that this is actually a process that many startups and companies and groups have to go through, where they want to build a blockchain, but they have to write all this other code about things like networking and consensus, but really all they care about is the state machine that they want to write, exactly what the logic of that chain is going to be. So Substrate is a framework for creating different kinds of chains in a much easier fashion. So if I speak a bit about our goals with Parity Substrate, we want it to be adaptable. So the idea is that you can upgrade the runtime of the chain. So when I say the runtime, I mean that actual state transition function, the code, the logic of the blockchain, what's actually getting executed when you run a block. And we want that to actually be something that can change without a hard fork. So it's adaptable, it can adapt to new requirements on the system. We want a first-class light client. Like, if any of you have tried to run a blockchain node for various different kinds of chains, you might notice that with a full node, it has such a strain on your system to download and verify all the blocks. And for some purposes, this additional level of security is actually necessary. But for your average user, you want a light client. And when you don't start with a light client, I can tell you firsthand, it is actually really hard to add one onto a code base. So we are starting from the beginning with a light client. We want governance. So governance, of course, is something that extends beyond the actual encoded logic of the chain. I mean, you can't get around the fact that the users of the system could just decide not to run that system anymore, could run completely different software. But there are many uncontroversial changes which are much easier to include if you have some form of on-chain governance. So Substrate does support chains which have that kind of governance. We want to talk about the idea of progressive consensus. So when we speak about when a block is finalized and won't be reverted, we want a consensus algorithm which sort of does this slowly. Like, we actually have a very powerful tool in a blockchain, which is that every block references the entire history of blocks before it. So when you integrate this into a consensus algorithm, you want one where you actually leverage this property that a signature on one block from an authority, from a staker, from a validator, actually provides security on all those blocks that were before it, that this is an economic attestation to the validity of that block. And lastly, in the context of Polkadot, we wanted Substrate to be something of an on-ramp for parachains. So if you decide to write a parachain for Polkadot, this library for writing general blockchains with Substrate is probably going to be fairly similar to the API that we need to write parachains for Polkadot. So now I'm just going to dive into basically how does Substrate work, how do you use it, and maybe even some more of the technical details if I have time. I don't know exactly how long this can run, so you can just cut me off whenever. But
as long as you want, man.
A warning would be nice. Okay, yeah, let's go. Let's get right into it. So we wanted to use a stack of technologies that's sort of at the cutting edge of various industries. So from a programming language side, we're using Rust. So Rust is something that we use a lot in Parity for the past several years. We're all Rust enthusiasts. I think actually at Socrates, you're also using Rust, right? Yeah, good for you. Rust is a programming language that has all kinds of static checking in its type system, basically to make sure that before the program is ever run, you've eliminated entire classes of errors that are very common in other programming languages and that can have potentially disastrous consequences. But the code still runs fast, so it's very suitable for systems level programming like Substrate. From a performance perspective also, we are using WebAssembly. So when I said you can write and upgrade the runtime of a blockchain, that runtime, this actual logic of the blockchain, the business logic, I guess, it could be transactions or smart contracts, you were to write this in WebAssembly. And this is something that's being pushed forward quite a lot by the browser vendors, as well as optimizing compilers like LLVM. So this has very good support even beyond the cryptocurrency space. It has a lot of eyes on it, and it's been in design for the past several years. So it's actually quite stable at this point. It's very usable for this sort of thing. As far as peer-to-peer networking, we're using libp2p, which is something that the guys over at Protocol Labs have been developing for the past while. It's meant to be a very general peer-to-peer networking framework, so we're using that for Substrate. And we're also, another nice side effect of the WebAssembly runtime is that you can run the exact same code in JavaScript as well, because of course WebAssembly is something that comes initially, at least, from browser land. And in browser land, they want all this WebAssembly stuff to be compatible with JavaScript. So we can write the same exact logic for the blockchain, and you can run it natively on a computer, but you could also run it in the browser, and that's actually a very powerful thing. And of course, we are, we'd like to get more teams involved with this. So please reach out if you find this interesting. So just as a diagram, here are some examples of different kinds of runtimes at the top. So the runtime is its own, basically, application-specific code. So we have one runtime that's for the Polkadot relay. And this is a completely separate chain from something like the EWF chain. But they're both built on this same technology stack. So that Substrate technology stack is using libp2p. It's using our own Rust WebAssembly interpreter that we call WASMI. And this is all, of course, written in Rust. So as a diagram, I guess, of the architecture of the system, at the top level, we have the actual runtime. So this will include whatever business logic of the chain itself. It'll have modules for governance, for staking, for parachains, permissioning, smart contracts. We intend to make this modular to the point where you can probably get basic things going just by plugging and playing with various pre-written components and maybe writing a little bit of glue code to tie them together. Those are all running in WebAssembly. We have a consensus layer that provides agreement over them, and we have libp2p that allows the consensus layer to actually do its work. So basically, all of this stuff is written in Rust. Some of it is WASM only. Some of it is built into WASM and run as native code. And some of these components, like the consensus layer and the libp2p networking, are obviously not accessible directly from the runtime, but are running as that native binary. So just a few technicals about things that we're using in Substrate. So taking from lessons learned and such when writing other blockchains, we're going to use ED25519 for authentication for digital signatures. So this is commonly regarded to be basically the best thing you can use right now. It's got a lot of really nice properties for security. It doesn't use random data, random inputs when signing. We're using the Blake2B hash function. We've got all this other stuff. One thing that's really cool is we've got an implementation of this very often overlooked random number generator. Which, a lot of you have probably heard of this issue of getting randomness beacons into blockchains. So whenever you want to do some kind of shuffling of validators on a proof of stake chain where you're randomly choosing who's next, you need a random number generator that everybody can agree upon. So this collective coin flipping one is one that's not really looked at that often, but it's essentially using a process that I'll call iterated majority of looking at previous block hashes. And there's a really nice paper of this exact title which does an in-depth analysis of exactly how much an attacker can influence that random value that comes out in the end. For a consensus algorithm, we're using a hybrid PBFT and OR-AND consensus. We've got some address format and a bunch of runtime modules that you can sort of string together. Yeah, so this is roughly what the execution path of a runtime block, of a substrate block looks like. So we have our WebAssembly runtime, which is running in a WebAssembly interpreter. It has access to this storage database where it can basically put any kind of data it wants. It might be account data, it might be UTXOs, it might be commitments to some kind of zero-knowledge payment scheme. And then you also have your native client environment. So when you write something with Substrate, of course, you will want to have very specific application code written around it. And this will also be native, but it'll be for things like providing APIs to developers and stuff that you just can't do in a purely general way. So there is an optimization here because WebAssembly is pretty fast. You know, it's faster than something like the EVM. It's actually been optimized. But when we execute blocks, we don't want to always be calling through WebAssembly. So if your Substrate node is up to date, it will route the block processing logic through some kind of native code, which is exactly equivalent to the WebAssembly runtime, which is on chain. But if your Substrate node is not up to date, it will fall back to the WebAssembly runtime, which is kept on chain, and it'll continue to process blocks correctly, but at a slightly slower speed. So the nice thing here is that even if you don't update your node still contributes to the network by continuing to validate blocks, continuing to propagate blocks. But if you do keep your node well updated, it'll do the same, but faster. In terms of external APIs, really, you have a lot of them available, but the most important ones are just get storage and set storage. So you have a runtime which gets and sets storage, it reads it, whatever. And there's a special key called :code. And if you are executing, say, a transaction, and you set this storage, then at the next block, it'll be running the new code that you just set. And that's how we do runtime upgrades. So usually you would build some kind of governance model, which actually guards exactly how those changes to that storage entry can be done. But you could probably write something that lets anybody change the code. It's up to you. It's pretty free. So these are the API entry points if you want to write a runtime. So there's one if you want to execute an entire block. There's one if you want to get the current list of authorities in the proof of stake system. There's these three, which are essentially used during block authorship. So if you have a whole block, you can just execute the whole block at once. But if you have to execute a block as you're building it, then you have these three. So first initialization, then applying extrinsics. So extrinsics are basically like transactions, but it's a generalization of the concept of a transaction because we don't actually know for sure that what people are writing with Substrate trains are actually transactions, right? It may be something that's fully automated or not even something that you could really consider a transaction. So we use this term extrinsic to generalize over that. And then lastly, to finalize a block. To talk a bit about our consensus, this is something we've been researching for a while in-house. So it's basically a hybrid model. So many of you have probably heard about things like finality, probabilistic finality. So this is sort of how we provide those things. So first we have what I would call a predictable chain growth algorithm, where we have authorities from the validator set randomly chosen, and at every block, and then they get to issue a block. And this is how you get the chain growth, and then we can prove some things about probabilistic finality over some period of time. But then we can use this probabilistic finality as a decentralized broadcast mechanism for blocks that are sufficiently old that we can run some kind of vote to get full finality on them. So that's what I mean by hybrid or-and PBFT consensus, just that this or-and portion is providing growth of the chain, and then behind the head of the chain, we provide finality on those blocks. And finality means that those blocks will never be reverted, whereas probabilistic finality just means, assuming that these guys aren't misbehaving and that network conditions are good, then this block will never be reverted, and that's actually a much stronger guarantee. Well, probabilistic finality is the weaker guarantee. Actual finality is the stronger guarantee. So here's a little bit of a diagram of how that might look. So we have blocks. This is, it's a complex system, so this diagram doesn't cover it fully. But essentially, each block has a distinct author, and those authors are chosen randomly in proportion to their stake. So if you have 10% stake, you're twice as likely to be selected as someone who has 5% stake. Although the way that we actually think about it is not in terms of stake, but in terms of weight which is a generalization over stake. And then behind the head of the chain, we're running this PBFT, so full finality. So you see this block here may be reverted, although this one may not be. And imagining this hadn't happened, then these blocks here were not necessarily going to stick around until this one was finalized, which thus finalized all of its ancestry. So that's roughly how the consensus in Substrate works. So this part is going to get pretty diagram heavy, and I can see the eyes glazing over. So if it starts going too long, just let me know. So the basic header format is just three things. So we have a parent hash. This is necessary to establish that linked list in the blockchain. We have the extrinsics root, which is the root of a Merkle tree, which is an ordered mapping from index to the actual extrinsic in the block. And then we have the receipt hash. So the receipt hash is just a hash of some structure that contains what we would call receipt data. And receipt data is sort of describing what happened during that block, and it enables us to run a secure light client by sort of comparing cryptographic references that are kept in this receipt to data that we received from peers. But these three things together are 96 bytes only. So even if you keep a lot of them on a light client, a lot of history, it won't use too much space. So we really wanted to minimize how much space that uses. Although, in fact, if your consensus algorithm is designed correctly, you don't actually need to really keep that many headers around for a light client. So the block structure, just to diagram that out, we have the parent hash pointing to a previous block. We have the extrinsics root pointing to some tree. And then we have the receipt hash, which points to this receipt structure. So that stores the block number. The storage root, so the storage root is the root of a Merkle tree containing all the storage. We have the changelog root, so we have the root of a tree which refers to all the storage entries that were changed in that block. And then we have a digest. So a digest is basically Substrate runtime specific information, which can be used to communicate things about validator set changes or signals of future validator set change, so that light clients can follow those correctly even without having the full storage. So the digest, as I said, is can be anything. The nice thing is with signals, if you signal a validator set change, for example, then you can do a warp sync where you have a block that signaled a validator set change, you provide a proof of finality of this block, and then so on and so forth, because the finality is always under the next validator set. And you can, under certain security assumptions, you can skip basically directly from the genesis or some checkpoint to the head of the chain. So, so here's the block structure again, pointing to the extrinsics, then the receipt hash pointing to this receipt structure, and yeah. So I guess I can skip through most of this just to talk really briefly at the end about the changelog. So one thing we have noticed is that on a light client, you typically want to track some kind of storage that's changing over time. So whether it's a balance of some kind or, I don't know, some kind of contract state, whatever it may be, you often on a light client want to track that change and be notified of when it's changed. But what you don't want to have to do is every time you get a block, then have to go to a peer and ask them, did this change? And not really being able to get any kind of definitive answer of whether it did or didn't, depending on if that peer is behaving maliciously. So we include a changelog, which basically just keeps track of all the things that have changed in that block. And then every 32 blocks, we keep another changelog, which keeps track of all the blocks where different keys changed. And you can do this in a recursive manner, so that once every day, you can check if a specific key in the storage tree has changed, and then find out. And you can get a proof of either existence or non-existence. So in that way, you can actually track the storage correctly. And yeah, So here are some just quick examples of potential runtime designs. So you could do something with Turing-complete smart contracts, right? So these smart contracts would be running WebAssembly. I mean, you could use some other virtual machine, but you would have to emulate it in WebAssembly, and then you would get into the situation of a virtual machine running a virtual machine, which probably isn't the best thing for performance. You would probably be using the account model there. You could run it with permissioning, for example. And you could do sharding there, but there would have to be some friction because the shards wouldn't be native necessarily. They would have to be emulated as WebAssembly smart contracts, and then you'd always have to run them as WebAssembly. You could have some kind of zero-knowledge-based privacy coin. So I was modeling a little bit on like the initial baby ZOE experiments that were done, where you just keep some kind of commitments, and then a light client can track when certain serial numbers were spent. For example, if they broadcasted a transaction that was supposed to spend that serial number, and you would do all the cryptography stuff in the runtime, and that substrate framework around it, things like peer-to-peer networking and consensus, wouldn't have to change any of its logic because it's completely abstract. And you could also do some kind of distributed collation, transaction collation protocol like the Blitz network. So that's where you have every account has, for every period of time, some other account that's responsible for it. And using that, you can get interdependent orderings where they matter, but not always have to worry about the exact ordering between transactions that happened on different accounts unless they coincide somehow. And lastly, this is Parity's plan for this, but by now you may be able to see that this is actually a very general framework. Parity would like to do the first Polkadot network implementation using Substrate. So it might support some kind of WebAssembly smart contracts. It might have limited app utility, but it would be a sharded chain where you had many different parachains advancing in lockstep, and it wouldn't have necessarily a firm upper limit on how many transactions could be done per second, assuming you can take the right latencies into account. Yeah, so I guess that's, no, there's some building blocks too. There's more. There's always more. Yeah. Yeah. Let's talk questions, please. I mean, it really depends on network conditions. So, and also on how many validators you have, because you're always going for this like 2/3 + 1 threshold. So if you have 1,000 validators, it'll obviously take much longer than if you had 10. But if you just want to speak in terms of how fast can we pass around these messages, a few seconds if you have a small amount of validators. But it really depends on how many authorities you deploy.
What was it for the PBFT?
For PBFT, I mean, just, yeah, a few seconds. It really depends on how you have a number of different variables. You have things like network latency, number of validators, but also how heavy the thing that they're trying to finalize is, so how much computation is done there. Because before you vote, you have to actually do the computation to see what you're voting on. But it should be within a few seconds, assuming you're not doing prohibitively large computations. But again, I can't really give numbers until you say exactly what your use case is. Yeah.
How is transaction ordering determined? You have, for example, this cryptographically secure pseudo-random number generator.
Yeah.
But does the miner have or the validator have the option to withhold the transaction?
Yeah. So one thing that's always runtime specific is block authoring. So we do want to provide a few libraries for that, but essentially, unless you know exactly what kind of runtime you're dealing with, you don't know exactly which, say, transactions to select for a block. And then that's always up to the authorities. But assuming the network conditions are good and that you have some honest majority assumption, then you can prove at least some kind of censorship resistance. Because even if a malicious validator withholds a transaction when it's his turn, eventually you'll get a good validator who, under good network conditions, has had this transaction propagated to him, and he will include it.
I'm guessing the same with the blind front, right?
Yeah. I mean, there's no real way to stop that unless you can do something clever with your runtime and your block authorship model. But it's also up to you and Substrate, because again, Substrate doesn't really make any assumptions about how blocks are created. So if you have some way to prevent front running in block authorship, then it should support that. Yeah.
So you said that Substrate was a framework to build a node or a chain.
Yeah.
You have an idea, and I don't want to put you on the spot. Maybe this is not something you're optimizing for, but like how many lines of Rust code roughly do you need to put the pieces together and build your own, or
yeah.
for a dummy application? Order of
how many lines? Yeah. It depends.
I mean, say
exactly. But
this thing, right? Literally a dummy application. How much work, or a day's work, like a week's work, at this point?
At this exact point, we're still fairly early in the development stage, so we actually only really started putting together Substrate a few months ago. But for Polkadot, I think the amount of Polkadot-specific code, and this is not minimal, is about 10,000 lines or so. And everything else is under that Substrate umbrella. So I think if you want to do something super minimal, it would be even less. And our goal is that we bring even more of that out into libraries that people can just bring together, and it should take much less.
And would it then, sorry to follow, would it then sort of be native to run as a parachain in the Polkadot network as well, or is that logic that sits on top of Substrate?
So it's not quite the same because
yeah, I understand, but like do you intend that to be part of Substrate so that a lot of parachains are built that can join Polkadot?
Yeah, it should be quite close to write a Substrate chain and to write a Polkadot parachain, because they're both WebAssembly functions. It's just that parachains also have to deal with things like message routing and stuff like that, which isn't dealt with in Substrate because it's the root level. Yeah. Yes.
So first of all, I'm really impressed by this, and I've noticed that. So around this, you're kind of open sourcing it and trying to build a community around it. You've done the same thing with like WASME and the WASM tooling that you have. What's the philosophy around trying to get ecosystems around these projects that are independent of Parity or Polkadot?
Well, primarily at Parity, we want to build something that's actually useful. So when we have the opportunity to we want to use WebAssembly and we write an interpreter, it doesn't do anybody any good other than us, of course, if we just kept that to ourselves. But that's just not really the company philosophy. Like if we wrote that tool, we will make it open source. And the same with this. So we saw the fact that having this general framework would be useful for Parity's goals, but also it would be useful for a number of other people. And Parity has been in this community a long time. Like Robbie said, this is actually all about knowing people and knowing projects, and we know that other people are building worthwhile things. So it doesn't make much sense to not open source that when I know that there are valuable projects that can use it. Anything else? Yes?
Could you swap consensus even?
So it's something we've thought about. It's very hard to actually reason about consensus in a purely general way. But it is possible that in the long term, we might actually allow a portion of the runtime to be dedicated to specifying some kind of consensus and agreement. But then if you're at that stage, you probably have to rewrite all your block authorship stuff, all your networking code, and everything around the assumptions of that other consensus algorithm, unless it's fairly similar, at which point you're basically writing everything yourself. But to some degree, we would like to support pluggable consensus. I really like the idea. We just haven't devoted the time yet to figuring out how exactly that will look in the context of Substrate.
For people interested in building on Substrate, what are sort of the next steps and timeline, and then who should they reach out to?
Yeah, so as far as the timeline goes, over the next few months, we're planning to actually do this implementation of so right now, actually the consensus is only using PBFT. So in the next proof of concept, we're going to be moving over to this hybrid consensus. We want to build out a lot more libraries, like Rust building blocks for creating runtimes. as far as who to reach out to, I think you can reach out to me. You can probably reach out to Fabi over there. You can reach out to Gav. I don't know, whoever you're in touch with at Parity. Like, we're glad to hear about how you're interested in using Substrate. Yeah, but there's quite a lot of development work to still do on Substrate, and we're doing it sort of in lockstep with our development on Polkadot. So we'll build some portion on Substrate that now is useful for Polkadot, and then we'll work a bit on Polkadot to sort of push it to its limits and so on. And that's a process that we expect to be ongoing for the next few months at the very least, until the end of the summer. It's definitely in proof of concept state. But if you are the kind of person who likes to ride that bleeding edge, it is open source, so we are glad to help you if you want to do that.
Thanks, Rob.
Yeah, thank you. Thank you all very much.